Hi everyone, my name is Siyan and this is my partner.
Nicholas Pennsylvania.
And today we are going to talk about the life and mathematical journey of French mathematician Sophie Germain. And first we'd like to play a video for you to introduce about the history background of France at that time.
Okay, and this is a short video about a little comedic history of the French Revolution. Oops.
Living the high life at their expense for long enough, and that it was time for common people to run the country. Here with more details is Bob Hale with the French Revolution report. Bob.
Thank you, Sam. Well, sacre bleu me, if that isn't France, which it is, if it's not the 1780s, which it is, and if that right there isn't a very angry Frenchman, which it is, and he's got every right to be, because back then France was very much a country of le haves and le have-nots, where the posh people have fine food, fancy clothes, palaces and helicopters, while the poor people, like this chap, don't even have the bread on their table. But how can... What? I don't think I did say helicopters. But how do these poshos afford all that stuff, I hear you ask? Well, by taking money from poor taxpayers, like our friend here, and then borrowing even more money from other countries, which means that by 1789, France is riddled with debt, and most French people are penniless and hungrier than an alligator on the moon. All while King Louis XVI and his posh chums are living it up big-styling. Terrible, really, but I guess that's just the way things are, and there's not a lot you can do about it, right? Wrong! The commoners strike up a plan to remove the king and run the country themselves, which signals the start of the one and only, the world famous, ladies and gentlemen, it's the French Revolution! Vive la Revolution! Sorry, I get a bit carried away. And the revolutionaries don't hang around. They storm the Bastille, a famous old fortress here in Paris, partly to show the king who's boss and partly to steal a load of explosives. Oh! Well, that's angry mobs for you. So King Louis, fearing for his life, dresses up as a Russian aristocrat's butler, little bit weird, and runs off to hide up here in a place called something or other. A cunning plan that works this much. Yep, not at all. The king is captured, he's brought back to Paris and told that he's not in charge anymore. He keeps the crown, but he loses most of his power, influence, and helicopters. And that's what? I didn't say helicopters. And things go from bad to worse for King Louis. In 1792, France declares war on Austria, a neighbouring country who want the revolutionaries out and the king back in. So they tell the revolutionaries that if they don't put the king back in, they'll start doing some pretty horrible things to the French people. A very clever tactic that works this much. Yep, not at all. Turns out the revolutionaries just hate being told what to do. They completely ignore the threat, accuse the king of plotting with the Austrians and cut his head off. Then they cut his wife's head off. And then, frankly, they just get a little bit carried away. Soon they are cutting heads off left, right and centre, declaring anyone who doesn't agree with everything they say as an enemy of the revolution, a crime punishable by, yes, you've guessed it, having your head cut off. In fact, if we look at the head cutting off-ometer, we can see that somewhere between 16 and 40,000 heads were cut off in just 2 years. So many, in fact, that they not only broke our thingy, but they had to invent a whole new head-cutting off thingy called the guillotine. So, at that time, it was all cut his head off, cut her head off, cut his head off, cut her head off, until, finally, after 5 long years and lots of heads being cut off, the people of France said, stop cutting people's heads off! And they took the man responsible for most of the heads being cut off, Maximilian Robespierre, and yep, you've guessed it, they cut his head off. And that's the end of the French Revolution, the end of the French royalty, and if I don't get a cup of tea and a biscuit in the next 3 seconds, it might very well be the end of old Bobsy. Oh, thank you so much, thank you. Oh.
Well, that's something silly, and we thought we'd give you a little bit of laugh and a recap of high school history of France at that time. And about Sophie Germain, she was born in the year of 1776. That's a few years before the French Revolution. And France was a male-dominant society at that time. Women didn't get a chance to go to school or receive any formal education like men did. And Sophie had to overcome her parents' opposition and social prejudice against women. And she taught herself math to an undergraduate level. Yeah. And Sophie grew up at the time of French Revolution and the following Reign of Terror, where there's, from the video you see there's lots of things going on at France at that time. So her parents think it's best for her to keep her at home to get away from the dangers outside. So luckily for Sophie, her father have a big library with good collection of books. So Sophie started to exploring in the library and read about math and science books. At the age of 13, Sophie read about a book called History of Mathematics. where the author talked about Archimedes' story. And the author said in the following sentence, Archimedes would forget food and drink. His servant would have to remember them for him and would almost have to force him to satisfy these human needs. And what more dramatic was about how Archimedes died. There's a legend that Archimedes was working on the geometric problems on the sand floor. And there is a Roman soldier was intruding his city and was getting into his home and started to ask questions to Archimedes. But he was so absorbed on the work he was doing, and he didn't even notice the soldier was there, and he failed to answer any questions, which led to his death. And Sophie was so fascinated about this story. And she thought that math must be something so interesting that could keep a person away from doing anything else. And from that moment, she decided to learn math and become a mathematician. She studied Latin and Greek on her own in order to read Newton and Euler's work. And later, she taught herself Bezout's element of arithmetic, and she studied Coussin's book, Differential Calculus, before the French Revolution. Next slide. Here's something about her family. She was the second daughter to the French silk merchant, Emperor Francois, and his wife, Mary Germain. Sophie's father later became director of Bank of France, and he was quite involved in the French Revolution as well. Although her family was quite wealthy, but they were not considered as very noble. And this is probably part of the reason why that she hasn't got a chance to a private tutor, nor her work were recognized during her lifetime. And at first, her parents was opposed to the idea that she's interested in math. But because math was a profession for men at that time only. But after knowing that she was so determined, they finally gave in and they supported her financially on her work for her whole life. Sophie was never married, she didn't have any children, and she didn't get any jobs. And she stayed home most of the time and worked on mathematical problems. And here is just something interesting to show you how she determined she was. Because her parents didn't allow her to learn during daytime, so she kind of sneak at nighttime and read a book after her parents went to sleep. And her parents find out about it, and they try to stop her by taking away her clothes, lights, and heat from the room because Paris had very cold winters. But she continued anyway. She wrapped in her beddings and still getting up and read under the smuggled candle. So that's how she finally got her parents convinced. Sophie became more publicly known after the year 1794, where she managed to get some class notes from École Polytechnique, which was the best university in Europe at that time. And but the university didn't accept any woman, so she had to get these class notes in order to learn more advanced math. And she started to writing to one of the professor Lagrange there under the name Monsieur Leblanc, who was a registered student. And so Lagrange found Sophie's work quite amazing. So he actually requested to meet her in person. And that's when he knew that there was Sophie that's been writing to him. And he visited her at home and complimented on her work. And two of them became friends. And Lagrange inspired lots of Sophie's work in later life, mostly number theories. And in 1798, Sophie became interested in another mathematician, Legend's theory of numbers. And Sophie started to write to him on number theories and later on the work of elasticity. Two of them kind of communicate their ideas quite frequently. And he became another mentor for Sophie. He even included some of Sophie's work in his own published paper on Fermat's last theorem, where he proves that n equal to 5. And in 1804, Sophie started corresponding with another mathematical giant, Gauss, on number theories. It was also under the male pen name Monsieur Leblanc, because he thought in that way Gauss can give the respect and actually read his work. It was not after 3 years later that Gauss found out it was a woman that he's been writing to after a little incident, because Gauss, at the time, Gauss, I believe, was in Prussia, where the French revolutionists went to Prussia and want to take over. And Sophie heard about it, and she was afraid that same fate of Archimedes will happen to Gauss. So she asked a favor of one of her father's friend, a general who's in charge, to check on his safety. And the general went there and went to Gauss and just gave out Sophie's name. But Gauss was confused at the time because he never thought he knew a person named Sophie Germain. And Sophie wrote him a letter, later confessed who she really was. And Gauss replied a letter to Sophie, quote, "When a woman, because of her sex, our custom and prejudices, encounters infinitely more obstacles than men in familiarizing herself with their knotty problems, yet overcomes these fetters and penetrates that which is most hidden, she doubtless has the most noble courage, extraordinary talent, and superior genius." So Gauss kind of held up high respect and esteem for Sophie. And unfortunately, two of them never met in person in life, and Gauss stopped writing to Sophie after year 1819, that his interest turned away from number theories. But two of them has been friends for quite a long time. And Sophie's work shifted from number theory to more applied mathematics. After in 1808, the German scientist Chladni made some demonstration of his experiment on the vibrating surface, which we will show you a video in a minute.
This is Sophie Germain's work in applied mathematics, and she did a lot of work with elasticity, which was up and coming at that point, which was actually solids. All solids have an elastic point, or most of them have an elastic point to where they will bend but not break, and that's kind of where the Eiffel Tower came into play. It was like a pre-design for all that. And she was actually, I think it was Legrand, he made like a warning, like a threat to this competition, and it scared away most of the male mathematicians of that time. They wouldn't even enter the competition. And Sophie, under her pen name, Monsieur Leblanc, she entered it, and they were looking at her work, and it was very informal. A lot of the integrals were wrong. She did the derivatives wrong and stuff like that, but she had the basic concepts down. And so they didn't accept her work. It was just not good enough because it was so informal. And this is a quick little video about some vibrating plates. Let's see if we can get a little closer here. Which is pretty cool. It shows you. I don't know if it has it.
In the late 18th
Yeah,
century,
it does have audio.
German acoustic scientist Chladni did a series of important experiments on the movements of thin plates. His technique was to spread sand or salt on these plates and then bow them with a violin or cello bow in various places and to observe the curious and beautiful patterns that emerged. The area where the sand or salt did not collect was being moved by waves. And the areas where the sand or salt did collect was, in effect, the nodes between these waves. The fact that these waves were being produced with a musical instrument, the bow, related the waves in the plates to sound waves. Chladni's achievement of relating sound and waves was a pivotal moment in the history of acoustics and paved the way for the development of the acoustical theory of waves.
All right, and just a quick representation. I'm going to do a little sketching, kind of like a visual representation of what kind of was going on. And what was that? So basically what he means when he talks about the nodes, so if you were like to drop a pebble in a pool of water, you have like your ripples, your ripple effect or whatever. And if you were to drop a simultaneous pebble over here, it would create the same ripple effect. But when you get these points here, this is where the waves are actually canceling out, and that's where the salt would be collecting, sort of. So when you have your plate, I guess it's kind of like just like so, and they're rubbing, the forces are here, so your waves are moving. And the way I like to think of it was like sine x over x wave, because it is dampening. It's not perfect, so you kind of have like this guy. So it kind of pushes it towards the edge, and towards the end, it'll slow it down. And let's see, I had a good representation over here. Yeah, and then, so basically it's stressing points, and it kind of tell you where this object is going to put out forces, or where it's going to move the forces to. So when you're talking about like a big building, and it stresses of a force pushing down on something, like where is it going to break if we have it built, you know? So kind of like that deal going on there. And that was most of her work in elasticity. She didn't really like it. She liked number theory a lot more. And it's actually the next slide, conveniently. She did a lot of work with Ramon's last theorem, which was trying to find like prime numbers. And I thought it was pretty interesting, because if you look at the xn plus yn plus zn equals zn, that's actually on our formula sheet for a cone. And except for it has no a, b, c values. And she basically updated it a little bit using P and the modules. And basically the mod, it's pretty hard to find a lot of her original work, because she just didn't receive a lot of credit for it. But let's see here. Oops, my bad. How did I do that? But she, for the most part, she invented a prime number machine, more so. And let's see here if I can, there's one more on there. Here's the theorems for it, which I'll explain on the board. Yeah. So all right. Okay. So we have, what is it? 30 PR, which is prime roots, is what this stands for. So your prime roots divided by 30. And basically, the two, if you have a prime number, P, right, you should be able to take your 2P plus 1, and this will give you another prime number, ideally. And through this machine, you're able to find most of them, and it's pretty repetitive, and it can go on forever, almost infinite amount of prime numbers. So you start out with the prime roots, and you don't use the numbers 1, 3, and 5, just because they're less than 5. She's trying to find, originally, Fermat had n less than 2, and Sophie Germain was able to figure out for n greater than 5. So, like, if you start out with 11, mod basically means, so if we have 100 minus 86, it's going to equal 14, right? So mod 7 means that 7 will go into 14 twice. This is basically here's your remainder, and this will go into your remainder. So it can be also written as 100 equals 2 mod 7. Kind of, it's really that simple. At first I was like, what the hell does that mean? You know? And so you have your prime number machine, and let me see here. So this is what we call the 11 series. So we take 11 as our prime number, and using mod 30, you basically have 11, 41, 71, 101. No, yeah, 101, and so we have 11. 2 times R11 plus 1 gives us 23, which is what they call a Sophie Germain prime number. And so we take the next one, 41. 2 times 41, which is prime number, plus 1. That gives us 83, which is also prime. So we also call that Sophie Germain prime. And then, so we go to 71. 71 is prime. So we 2 plus 1, and that's going to give us 143, which is divisible by 11, the original prime number, times 13 equals that. So this is not Sophie Germain prime, and that makes 71, what was it here? It disqualifies it for Sophie Germain prime, basically. And yeah, it's just a kind of a hit and miss thing. It just potentially repeats forever, and as you can see, they've used this to find the largest known prime number, which is 2 to the 57,885,161 minus 1, and it has 17,425 digits. And there's a funny little video just to show you how long it is.
Oh.
Oops, sorry. Oh no. Zoom it all the way. This Prezi thing's kind of new, so it's got a little weirdo bugs in it. Where is that guy? Oh yeah, we put it in the end of the slide. You see that number with 1 million digits, 17 million digits? You're not gonna watch this whole video. This is an extremely long number. And
Error.
thank you. No. And here's another really cool video I found that explained the geometry of Fermat's last theorem a lot better.
In the margin of an ancient book, the 17th century mathematician Fermat stated that the equation x to the n plus y to the n equals z to the n cannot be solved with non-zero integers x, y, z for any integer power n greater than 2, and then wrote, "I have discovered a truly marvelous proof that this margin is too small to contain it." The statement remains unproven to this day. Computer graphics can help us visualize the nature of mathematical ideas like Fermat's theorem. Fermat's equation itself is just a cone for n equals 2, and there are many integers, such as x equals 3, y equals 4, and z equals 5, that satisfy the n equal 2 equation. If we vary n continuously, the cone changes to an inverted pyramid. The slices at constant z are two-dimensional superquadrics with exponent n. Varying n swiftly interpolates between circles and squares. The curve passes through many integers as n varies, but somehow just misses hitting any integers for integer values of n, unless n equals 2, the perfect circle. Just as one can ray trace a deformed solid by following a deformed ray through the undeformed shape, we can deform the integer grid instead of the Fermat curve. Recent attempts to understand Fermat's last theorem have explored the relationships between number theory and the algebraic geometry of surfaces. Instead of looking for intersections of a cone with a 3D grid of integers, we look for intersections of a real 2D curve with points whose coordinates are ratios of integers. In this framework, Fermat's equation extends to a two-dimensional surface embedded in the four-dimensional space called CP2, the complex projective space of two complex or four real dimensions. For each n, the surface becomes a patchwork quilt of n-squared pieces that surround the origin and extend to infinity in two complex dimensions. To visualize what is happening inside the surface, we can sweep the surface out from the outside in, or cut into the inside, or use transparent displays. For each integer power n of Fermat's equation, the surfaces have the topology of spheres with more and more teapot-like handles. To see these as the closed surfaces they really are, we transform the surface so it lies within a compact sphere. The clearer our mental picture of the problem becomes, the more likely it is that we will gain intuitive insights that will finally allow us to solve the problem.
I just thought that was a pretty neat little. I don't know how to keep doing this. No more of that. And Sophie Germain died on June 27th, 1831, and was not forgotten. She has a prize in her honor that commemorates someone with breakthrough research in fundamental mathematics. Some like, linear algebra, which we may be taking in the fall. And here's a little list of things she did. Is this the wrong side? Yeah.
This is why we think that Sophie Germain is so remarkable as a mathematician, because most of the time she worked by herself. She didn't have any professional training to math, and she didn't have access to certain resources like the men did at that time. But she devoted her life to math, not because of money, not because of fame, but purely out of her interest in initiative. Yet she brings out some innovative solutions to Fermat's last theorem that she didn't really prove the specific exponents. Rather, she provided a grand strategy for the prime numbers. And she did something that no other woman has done before. She received a medal from the Institute of France, and she was the first woman who attended the Academy of Science other than the wives of scientists. Sophie received an honorary degree from University of Göttingen after her death. And I would like to conclude our presentation with the sentence that the historian Mosin comments on Sophie. She was the most profound intellectual woman that France has ever produced. Okay.
And here's our bibliography. And that is the end of our presentation.
Thank you for your time.